Dr. Bob Zubrin for inviting me to come here this morning and talk to you about one small part of what Bob just talked about, and that is the in situ resource utilization aspect of what we'd like to do on Mars. And I think Tony Muscatello will be giving a presentation later on today, hopefully with a little bit more detail. Yeah, I've worked at the Johnson Space Center now almost for 30 years, starting as a co-op in 1985. And I actually got involved in ISRU because of your sample return mission concept that came out of Lockheed Martin. I think that was in '94. The interesting aspect of it was that, and I digressed, I think I had the time. In 1992, a study was performed for a Mars sample return mission that required two Titan IV vehicles. One to land a large rover to go grab some samples, the other to land a fully fueled ascent vehicle to bring those samples home. For 2 years, and Bob Zubrin proposes that a sample return mission can be done with a single Delta II launch vehicle. That got a lot of people's attention, so for the first time the Johnson Space Center on the engineering side decided to take a look at it, and I worked in the propulsion branch here at Chemical Propulsion. And it got to the point where, up to this point, the ISRU work had been done on our science side for a large number of years. And I was tasked with designing the landing propulsion system and the ascent propulsion system. And they looked around and they said, well, who at Johnson in the engineering directorate knows how to make anything about the propellants? And they said, well, you're going to use them, you figure it out. So that's kind of how I got involved in all of this. And as Bob kind of mentioned, you know, NASA goes in fits and spurts, and so a lot of the work that you're going to see has been done over this time frame. So I always like throwing this chart up to kind of make sure that we're all on the same page. In situ resource utilization basically involves hardware and operations that harness and utilize in situ resources to create products or services that can be used for robotic or human exploration. And I use in situ loosely because our unofficial logo for ISRU and NASA is a vulture, based on the fact that trash or waste or whatever anybody else throws out is a resource just as much as the atmosphere of Mars and water ice at the lunar poles. We typically break this down into 4 or 5 different areas of research. The first being making sure we understand what those resources are. Basically, you know, prospecting. Go out, characterize, map, make sure that the resources are there, they're in the form that you expect them to be, they're in the quality and the quantity that you hope that to use. Basically, mining principles 101. Once you have an idea of those resources, there are several things you can do with it. The one that we are primarily interested in is mission consumable production, making propellants, life support consumables, fuel cell reactants, things that get used up. And as Bob pointed out, you know, launch vehicles are primarily propellant, chemical propulsion stages, and such. So then, but there are other things you can use it for. Civil engineering, surface construction, making roads, landing pads, berms, habitats. Some of these things are actually very important when you start thinking about going back to the same location over and over again. I had the opportunity to go to a nickel mine in Sudbury, for example. They build roads a mile deep under the surface to get to the ore body fix. They don't do that because they like to build roads. They do that because it cuts down on the maintenance of the hardware traveling back and forth from the ore body. So these kind of things may be important. In situ energy generation. At the moment, Apollo was a great mission. It didn't reuse anything. It brought everything with it. At some point, we find that in many missions, they're power limited. So coming up with ways of actually generating and creating power from the in situ resources. It could be something as simple as finding water and turning it into oxygen and hydrogen. We've had work look at solar array production on the lunar surface as well. And then in situ manufacturing. This is an area that really is going through a revolution with 3D printing as a possibility. Now, two things that I try to point out to most audiences, especially those within NASA, is that ISRU is a capability that involves multiple technical disciplines. A lot of times, you know, people try to pigeonhole, oh, that's ISRU, and this is life support, or this is robotics. To a certain extent, ISRU encompasses a lot of these different areas. But there are certain technologies that are purely maybe ISRU, but we have to leverage and work with others. The other is that ISRU does not exist on its own. A lot of times we get into the situation where it's a chicken and the egg. We've never demonstrated ISRU, therefore I won't put it on the first mission. I'll demonstrate it first and we'll add it later on. But when you add it later on, you've over-designed your mission and it's not in the critical paths to getting that mission done, so why spend money on ISRU to begin with? So from the start, it's incredibly important that these customers, whether it's propulsion systems, life support systems, habitat systems, recognize that the products and services that can come from ISRU are there so that they don't design over them. For example, closed-loop life support systems on the water surface. If I'm making propellants, if I'm grabbing water from the soil, I don't need 100% closed-loop life support system. So what are the resources? This is just a very top-level chart, educational-wise. Bob mentioned that almost 50% of the lunar surface has oxygen in it in some form of oxides, metal and non-metal oxides. There are 4 major resources on the moon that we've considered. The regolith, again, is the primary one. Some solar wind volatiles. The moon has been hit by the sun for billions of years, and primarily protons in the form of helium, or hydrogen and helium and such. Those are mineable. You may have heard of helium-3 mining as a possibility. Over the last decade, more and more data is coming in that there may be water ice and other very interesting volatiles at the lunar poles, on the order of several percent, 5 plus or minus 3, or if you talk to Dr. Paul Skoudas, there are thick layers of ice noses. On Mars, we have an atmosphere, and the tenable is very thin atmosphere, but it's primarily carbon dioxide, a very accessible resource anywhere we land. There's lots of oxides, especially iron oxide from the color that you see, which is very similar to one of the simplest processes of lunar ISRU, and that is taking the oxygen out of iron oxides with hydrogen. But what's been really interesting over the last decade or more, again, is the water on Mars. Viking gave a preliminary answer of something on the order of 2 or 3% water, so people thought, okay, Mars is bone dry as well. We've been learning through orbital data that that's not the case. I have a chart later on. Phoenix basically showed that there's dirty ice at 70 degrees north latitude. So water becomes an incredibly interesting potential resource, as well as the carbon dioxide in the atmosphere. This chart is basically chemistry 101 for Mars. There are many things that you can do with carbon dioxide and hydrogen. Our whole petrochemical industry just down the road is largely based on some of those things. As Bob pointed out, if I'm only interested in the oxygen alone, there are several processes that I can use. The simplest is taking the carbon dioxide and actually electrolyzing it into oxygen and carbon monoxide using a solid oxide electrolyzer. We also use a reverse water gas shift reactor. where you take carbon dioxide and hydrogen, and it makes carbon monoxide and water. And then you basically, as pointed out, electrolyze that water into oxygen and hydrogen and recycle it. And so it's a closed loop system other than losses. And then there is actually a process called WASH, that takes the carbon dioxide and hydrogen, leaves solid carbon behind, and gives you twice as much water as possible. That may be of interest if you need carbon for building materials or graphite or something like that, but it's usually very difficult to deal with the carbon after a period of time. If you want fuels, the simplest is methane, taking carbon dioxide and hydrogen, as Bob mentioned, in what's called the Sabatier reactor, makes methane and water. You can do similar reactions with carbon monoxide as well. And then there's basically a lot of work has been going on where if you take carbon dioxide and water together through an electrochemical reactor in one unit versus two separate units, you can spit out oxygen and methane. Methane is an interesting fuel. I have the chart on that later on as to why we pick methane. But if you're interested in heavier hydrocarbon or methanol or alcohol or something else as your preferred hydrocarbon, there are, with carbon monoxide, carbon dioxide, and hydrogen, you pretty much can make anything you want with a Fischer-Tropsch reaction or something else along those lines. And then there's the splitting of water, as I mentioned. You can do that through electrolysis. You can do steam reforming of your fuel, methane, to try to get back some of that hydrogen if you didn't want the methane in the first place. Or you can take methane and carbon dioxide and do some dry reforming. When we look at human missions from Mars, there are basically 4 propellant production processes that we've considered. Making oxygen and bringing your fuel through that first 2 processes, either electrolysis or reverse oil gas shift. Making the oxygen and your methane or hydrocarbon fuel by bringing hydrogen from Earth, as was done in the first Mars Direct. Now that we think that there's significant quantities of water, the 3rd process is don't bring hydrogen, dig up the soil as well for your hydrogen source. And then the 4th is, hey, I got oxygen, or if I have water, why use the atmosphere? I have oxygen and hydrogen propulsion systems. Each one has strengths and weaknesses. There are other propellant options that have been considered for robotic missions, but not necessarily for humans. That deals with carbon dioxide itself. I think you've had the nuclear carbon dioxide hopper option, where you just literally take carbon dioxide, run it through something that will heat it up. It's very low performing, and then it allows you to hop to another location. Great for surface applications and robotics, not really good for getting off the Mars surface. Other people have proposed taking metals, magnesium, aluminum, and burning them in carbon dioxide. Possible, but not likely for a human mission. So I've highlighted 3 particular processes. Those were ones that we looked at the Mars Design Reference 5.0, and was making only oxygen and for the first 2, and then oxygen and methane using carbon dioxide and water using the Sabatier reactor and water electrolysis system. Now, for the last Mars Design Reference Mission 5.0 was the first one to actually think about using water on Mars as a resource. Design Reference Mission 1 to 4 only assumed processing the atmosphere and in most cases bringing hydrogen. So for this time we looked at, okay, if water is a resource, what does it take to do that? And what we found was very interesting. Overall, the baseline option that was considered the lowest risk was just making oxygen and bringing the fuel. You still save 25 metric tons compared to bringing your propellant with you. And as you look, where's the, see if I can do this without burning anybody's eyes out. From a mass-wise, it was the lowest risk, but it was the highest mass. And most of that is the 6,500 kilograms of methane fuel that you're bringing to Mars. And there's a small plant for making the oxygen, something on the order of 500 to 700 kilograms. So then we started looking at what does it take to process the soil, and this was done back in 2007 when we were just starting to do work on lunar ISRU. And so we thought we needed to heat the soil up to around 600 degrees C or higher to drive off the water. And we looked at very low concentrations, 3% water and a reasonable 8% water, based on the Viking results at that time. And we were told by the planetary protection folks, by the way, you're only allowed to skim the surface of the soil because there might be life below it and you're not allowed to go towards that. So we said, fine, we'll just do that at this point anyway. What we came up with was we did need more power, but the mass dropped significantly, and so we really liked the 3 to 8%. Now, even though the power number jumped out at people, I need twice or 3 times the amount of power, we're talking a nuclear reactor. So for the 25 kilowatt power range, we needed a nuclear reactor on the order of, I think, 7,000 kilograms. For the 50 some odd 60 kilowatt reactor, that jumped up to a whopping 8,500 kilograms. So jumping twice to 3 times the power, the size of the nuclear reactor growth was minimal. However, we're talking about mining on Mars versus sucking in the atmosphere, which caused some heartburn. We've not demonstrated that before. So we backed off and we said, okay, fine, we'll baseline the oxygen production from just the atmosphere, but we want to keep pursuing this water processing on Mars. Now, why do you want to make propellants? Why is it so advantageous? Well, Bob kind of alluded to this along with, the fact that if you have to bring everything along with you, that makes your transportation system bigger, which makes how much more propellant, which, it's a spiral. And a lot of times when I talk to high school students, I use the analogy of, imagine you're driving from New York to California and there's no gas stations or food places. Your car grows, that requires you to carry more gasoline, which requires, so you're basically at the end, driving a gasoline truck, across the country.
Yes.
So what's really interesting is if you work backwards and you say, okay, I've landed 1 kilogram of something on Mars. It takes something on the order of about 9.1 kilograms of mass and propellant for the entry, descent, and landing to get you down that one. It takes something on the order of 2.9 to 3 kilograms of propellant to get into the proper position on Mars. It takes another 8.5 kilograms of propellant to bump you out of Earth orbit. So depending on the type of propulsion systems you're considering and the type of trajectories you're looking at, for every kilogram you drop on the Mars surface, somewhere between 7.5 and 11 kilograms need to be launched into low Earth orbit. So if I'm making 25 tons of oxygen on Mars, that equates to something on the order of 187 to 282,000 kilograms of mass launched into low Earth orbit. That's basically 1 to 2 SLS launches just by making propellant on the Mars surface. So that's really why we focused so much on this versus the civil engineering aspects in many cases. The biggest bang for the buck. So why methane fuel? Basically, it's a combination of things. First of all, it's very, from an ISRU person, if we had to pick a fuel to make, methane's probably the easiest. It's very simple, single or two-step process, and you get extremely pure product, high conversion efficiency of carbon dioxide, hydrogen to methane, greater than 99% in some Sabatier reactors. So it's a fuel that you can quantify very readily and give to somebody and say, I expect always to have this level of purity in the product. From a propulsion point of view, there are pros and cons. It's a fairly high specific impulse. We use the term ISP. It's basically your miles per gallon kind of aspect when you consider propulsion engines. And you know, chemical oxygen hydrogen is the best chemical propulsion system. It's on the order of 460 to 480 seconds of ISP. Well, methane is up to 380, 365. So it's a good. It's also very clean burning, which is important from a propulsion system. Heavier hydrocarbons leave basically solid carbon behind. So for longer you're running the engine, if you want to reuse the engine, that coking could be a concern. It also causes some lower performance issues. The con is that it's a lower density hydrocarbon. It has to be cryogenically stored. But the interesting thing is that if liquid oxygen has to be cryogenically stored, methane has a very similar storage temperature. So the same technologies that I've designed for storing my liquid oxygen get stored into, I'll take questions. For the propulsion system, the oxygen that we make comes off as a gas, but then it gets liquefied and stored. And so from an overall choice, from the ISRU perspective as well from the propulsion system perspective, methane is a nice, reasonable choice of fuel. So now we're getting a little bit more into the ISRU processes, the atmospheric processing and the soil processing, the strengths and weaknesses. I've kind of mentioned the atmosphere is provided globally. From a propulsion system point of view, oxygen makes up typically about 75 to 80% of the mass of your propellants when you're dealing with hydrocarbons. And we've done significant research on those chemical processing, not only in ISRU, but in fuel cell and life support systems. The weaknesses, basically, if you're either having to bring your fuel with you or you have to bring hydrogen with you. The mass of hydrogen is actually pretty small. It's the volume that is really tough to figure out. It's basically 3 times the volume of the fuel, methane fuel, that you're carrying. Soil processing, the strengths that we're learning more and more about the surface characteristics of Mars. There's water in many different forms and fairly high concentrations depending on where you go. At this time, we had spent a lot of work on how do I excavate and process lunar soil to get oxygen and maybe some of these polar resources. Those same technologies can be used here for Mars water processing. And even at low concentrations, that 3% water case, we still had tremendous mass benefits compared to bringing our methane fuel. The weaknesses at this point, it's more complex than sucking up the atmosphere. We also get some local dependency. So if we're really interested in bopping around Mars and trying different locations, we may have to develop different soil processing techniques. What I use at the equator for hydrated soils is not going to be what I use up at a 60 or 70 degree latitude where I have dirty ice, for example. And then at the time I wrote this chart a while back, there were concerns about planetary protection in the search for life. You know, if I go to a wet location, am I, causing somebody else heartburn? And it's funny, there's a mostly science group called MEPAC, the Mars Exploration Program Analysis Group, where I used to go back in the 90s as one of the few engineers. And it was primarily aimed at the robotic exploration of Mars. And at one of the conferences, workshops, somebody mentioned about the desire to drill for aquifers on Mars to look for life, and why we needed, drills to go 1 kilometer down. And the scientists would say, and oh, by the way, it could be used for ISRU. So I raised my hand and I said, okay, you found that aquifer, you drilled down, you found life. Can I run it through an electrolyzer and kill it now? Everybody laughed. And then they sobered and the scientist said, no, you have to find another aquifer with life before you can kill this one. And I said, well, then it's not a resource. Water distribution on Mars. So here's some of the things that we've learned over time. This was a top level looking from orbit, a meter down. And so we have fairly hydrated water abundance at the equatorial sites up to and above 10%. We basically are seeing extremely dirty ice and shallow at the poles. It's just below the surface, as we saw. Phoenix's thrusters brushed off the surface and there was basically a slab of ice there. But we think that there's actually some reasonably low permafrost areas down in the 45 to 60 degree latitude. And then they're actually seeing ice lenses, pure craters of ice in some of these pictures on the Mars surface. So water is pretty prevalent. We just need to figure out how to mine it without people for periods of time. So what are the challenges that we face with ISRU? First of all, the resource unknowns. We do know the atmosphere fairly well, but one of the concerns that we've had has been a little bit with the dust. Dust is prevalent. Dust will get everywhere. And if I have filters, if I have valves, if I have catalytic systems at very high temperature, will that dust degrade those types of pieces of hardware? And the Mars 2020 mission that will fly will now include a ISRU package, and I'll mention that's part of the reason why it's flying, is if I run day and night on Mars or an extended period of time, will I see a degradation because of contaminants in the atmosphere or the dust? Water unknowns. Water is a significant resource. If we can get it, it's enabling in a lot of cases. However, what form is it in? What are the contaminants? When I heat up the soil and I drive off the water, is there anything else in the water that will cause a concern? When we started working on lunar ISRU, for example, the idea was to take lunar regolith, heat it in the presence of hydrogen at about 900 degrees C, and it makes water. And oh, by the way, there's solar wind volatiles, but they're at the parts per million. Well, what happened was we started to find out that there's very small amounts of chlorine and fluorine and sulfur. Well, hydrogen likes to react with those things, and we were creating hydrofluoric acid, hydrochloric acid, and hydrogen sulfide at very low concentrations to begin with. But as we were processing more and more of the soil, that started to build up, and we actually had corrosion in our system. So now we had to come up with a way of pulling those very small quantities of acids out to protect our system. So we need to understand those things. Long-duration autonomous operation. As Bob pointed out, our thought is we land our ascent vehicle, fill it up with our propellant before the crew ever leaves from Earth, making sure that they have a return vehicle that's ready for them. Well, that means it's basically operating on its own for 300, 400, 500 days without a crewman there to do maintenance, kick the side of the hopper or whatever. So we need to understand that. Plus, the time delay between Mars is something on the order of 8 to 40 minutes, depending on orbital mechanics. So if something goes wrong, it's got to figure out for you that it's gone wrong and safe itself or come up with another way. That plays into the reliability and the maintenance aspects, and then operation in the severe environment. There are places that we want to do ISRU that are dusty, have extreme thermal temperatures. For example, if I go to a permanently shadowed crater at the lunar poles, that's on the order of 20 to 100 Kelvin temperatures. 0 Kelvin is absolute zero, so it's fairly cold. And liquid hydrogen is at 20 Kelvin. So I'm basically operating potentially at liquid hydrogen temperatures. Recent and past ISRU technology efforts. So this kind of has gone in starts and stops. A significant amount of work was done in the 90s by Dr. Zubrin and others inside and outside the NASA community in terms of CO2 collection and separation. How do I get that carbon dioxide out of the Mars atmosphere? We looked at absorption pumps, basically solid materials that absorb carbon dioxide, as well as literally freezing the CO2 out of the Mars atmosphere. It's already fairly cold. CO2 freezes at the poles on a yearly basis, so it's a reasonably small delta T temperature change to potentially freeze out the CO2. Processing it. I mentioned on that Chemistry 101 chart a number of different things. Well, we've built CO2 electrolyzers, we've built reverse water gas shift reactors, Savadia reactors, methane reformers, different fuel reformers. Bob has been instrumental in trying out different things, toluene, benzene, methanol, to show basically that it can be done. And then we started looking at a type of, not only the reactors themselves, the catalysts, but how do you package them? There's an area of research called microchannel processing, where instead of a catalyst bed with pellets in it, you can come up with platelets and stack these catalyst systems and heat exchangers so that you can get 1 to 2 orders of magnitude mass reductions and much better reaction kinetics. Water processing, different ways of electrolyzing and decomposing the water, cleaning up the water from those contaminants that come out, as well as heating up the soil to drive off those contaminants. And because of our lunar processing, we have looked at different types of reactors on heating up the soil, getting oxygen out, volatiles. And in one case, this was a icy soil processing reactor. We've also not just worked on the technologies, but the systems themselves as well. It's one thing to have different technologies, as Bob was saying, the yard filled with interesting things that you bought, but you need to put them together and make sure that they work properly. We find that if you just focus down on one thing, I want to electrolyze the CO2, what's the best way of doing that? Well, that might not be the best way of working with your CO2 collection system, or okay, I've gotten the oxygen, but I want to liquefy it, and it's so, in the wrong state and such. So you really need to build these things. So we've built several generations of Savadia water electrolysis systems, reverse water gas shift systems, Kennedy and Pioneer Astrobotics, CO2 processors. Down here in the bottom, from 2005 to 2010, we performed significant research on lunar ISRU, extracting oxygen from iron oxides and silicates. And we actually took our hardware out to Hawaii on Mauna Kea, which has a tephra, volcanic ash, very similar in size distribution and to a certain extent some of the chemistry to the Moon and Mars. And we operated for a week to 2 weeks, digging up the local material, running it through all the systems. Our test in 2010 we called dust to thrust, because we dug up material, turned it into water, electrolyzed the water into oxygen, stored the oxygen, and had it basically a little 5-pound thruster firing into the soil. We actually even sintered the soil to give a little landing pad, so we were firing onto a landing pad versus the old soil as well. So we have done a lot of this, at least at the engineering scale. And as many of us within and outside NASA know, it's one thing to show a view graph of what you hope to do. It's another thing to bring NASA management out to the field, showing the hardware it's operating and saying it's just now a matter of engineering to reduce the mass of it or increase the production rate. So what's going on now? Sadly, we had a dedicated ISRU project within NASA from 2005 to 2011 that was attacking all of these things, technologies, putting them into systems, getting them out into the field. That program was canceled during the reorganization. So primarily from a technology aspect, we are performing what's called small business innovative research. We put out a call for proposals each year. Small businesses can bid on them, and the last several calls have been primarily aimed at trying to understand dust filtration, better methods for CO2 collection, better methods for CO2 electrolysis, and looking into microchannel Sabatier reactors. Last Thursday, it was announced that an instrument called MOXIE will fly on the Mars 2020 rover. It is designed to produce 0.02 kilograms of oxygen per hour, 20 grams, and operate for a minimum of 50 times on Mars. I'll mention the scale aspects in a minute. We have another project called Resolve that is a lunar prospector experiment to go to the poles, drill down to 1 meter deep, and look for water ice and other volatiles that may exist there, such as carbon monoxide, helium, and such. And then there are several what are called advanced exploration systems projects. These are low-funded but civil servant heavy type of activities to basically start looking at the hardware. There was one called Trash to Supply Gas, where the idea is take crew waste and turn it into oxygen, water, and propellant. Pioneer Astronautics had a very successful SBIR on that subject for steam reforming and oxidation. And then we're in the process of proposing a new start for a Mars ISRU project. It actually combines ISRU, fuel cells, life support, and cryogenic storage called MASTER, with a hopeful new start this fall. So when it comes to production, propellant production on Mars, there's two aspects. There's what's needed and what's been demonstrated. And there is a difference between the two, a gap that we need to fill. So what's needed? For the human missions, typically we need something on the order of 20 to 25 metric tons of oxygen to get into a higher Mars orbit, not direct Earth return. That requires something on the order of about 2.2 to 3.5 kilograms of oxygen per hour, 24 hours a day for 300 to 400 some days. If we do a sample return mission, there's lots of different sample return missions, small ones, large ones. One of the things that we're looking at is, can I use a sample return mission as a dress rehearsal for this human mission? So we're talking about something on the order of 0.5 kilogram to maybe 1 kilogram of oxygen production per hour. You know, 1/4 scale of what I might need for that human mission. Work out all the bugs and a non-human mission critical activity, launch it off the Mars surface to show that I can store it and use it for propellants. And then there's the Mars 2020 demo, which is 0.02 kilograms. So you see we got slightly 2 orders of magnitude, if not more, production rate that we need to kind of work on. What's been demonstrated? Well, most of the stuff that we've done in the lab has been actually in the very small scale, 0.02 kilograms per hour to 0.08 basically. Most of it was aimed at very small sample return mission class type of activities. We started a project a number of years ago called Marco Polo. where we started to try to get higher up in the production rate. We have a water processor that can get us that ½ kilogram of oxygen per hour, but our Sabatier and CO2 collection systems are a little bit too small. It turns out our soil processors that we've developed for lunar ISRU are in about the range that we want, the 5 to 10 kilograms of soil processing per hour will get me enough water to go between ½ kilogram and 1 kilogram of oxygen per year. So we're trying to basically leverage that hardware now. As I kind of mentioned previously, you really want to have ISRU done up early for all these different customers, because it basically influences the architecture choices. The power system that's used on rovers and EVA suits and such. If left on their own, they may pick batteries or something else, whereas, you know, what type of fuel cell would we use? Hydrogen, oxygen, or methane oxygen fuel cells. Science, actually, there's a lot of synergism between science and ISRU, trying to get subsurface samples, providing them consumables for science and such. And then the big area is life support. You know, the different technologies, giving life support people extra water and oxygen, but taking their trash, what they don't want, becomes a resource to be fed into ISRU. So one of the things that we've been pushing is to now start thinking about this commonality, integration of systems when you consider ISRU. If you look at Apollo, if you look at Shuttle, and to a certain extent if you look at Orion, all of these spacecraft have propulsion systems, power systems, life support systems, thermal control systems. You have a different team for each one of those. And each team puts their blinders on and say, how am I going to give the lowest risk, lowest mass, lowest cost thermal control system, life support system, propulsion system? What you find is, you know, your thermal control system uses ammonia, your propulsion system uses nitrogen tetroxide, your life support system uses oxygen at a certain purity and requires 3,000 psi for EVA suits, and your fuel cell power system used supercritical oxygen and hydrogen. Can we all come together and have one type of system where, for example, if I have a regenerative fuel cell, I need water electrolysis. If I have ISRU, I need water electrolysis. If I have life support system, I get water electrolysis. I got to store all those consumables. So if I can have this kind of a system, potentially I have reduced the overall system mass, complexity, cost of developing all this hardware, and such. And so this is where we're trying to aim to over the next several years. This is the end chart of that master program, where we're trying to take ISRU modules, habitat life support modules, cryogenic storage and transfer. How do I store and transfer oxygen and methane in a dusty environment without losing any of it? If you notice launch vehicles, typically you'll see a vent stack going on. If I've spent 300 days making that oxygen, by God, I'm not going to vent it while I'm filling the ascent vehicle. I'm going to capture it and recover it and use it. So basically, how do we get all of these different communities working together at a common production rate and minimizing the technologies overlap that's being done by all of them? With that, I come to a conclusion on my presentation. Sorry if I'm ending a little bit early. There's two charts I want to show before I get going. One of them is, why are we doing a demonstration in 2020, and why do we need working on ISRU now if we're going to fly, hopefully, humans to Mars in the 2035? So this was a chart I put together a number of years ago that said, okay, we're flying to Mars in 2035. Loads of time to develop technologies, isn't it? Well, not really. When you talk about human spaceflight, there's reviews. You got to get your technologies up to a certain point. And basically, you need to be at what's called TRL 6 you've proved out the technologies enough that you're really comfortable with them, something on the order of like 10 years before you're launching. So that gets me to 2026. So I say, well, how do I buy down ISRU risk so that 10 years before I launch humans and I'm inserting this technology into it, they're really happy that I can do these things. Well, that's where the Mars sample return mission concept came in. If I fly that in 2026, I've demonstrated everything. It goes into that mission. Well, we're back in time. To do that mission, I'm basically starting in 2019, 2020 to have that mission in 2026. So then the last question was, well, that actually mission now becomes a little bit important. What can I do to buy down the risk of that? What are the risks? Well, I really want to know about the atmosphere and contaminants and dust, and showing that I can demonstrate, even if it's at 20 grams per hour. And so that's kind of where that led to that desire for having the demonstration. The last chart I think is really interesting. The Curiosity rover has basically an instrument called SAM, Sample Analysis on Mars. And it's a science instrument primarily aimed at understanding the rocks and such. But their first sample that they put into it was just literally scooping the surface and throwing some dirt into it. So we knew it was going to be fairly desiccated. But what's really beautiful about this is they did a temperature profile. How, as you heated up the soil, what got driven off, at what point, and in what concentration, all the way up to 900 plus degrees centigrade. Well, we see this beautiful water curve, and it gets driven off really early, and the bulk of it actually is driven off before 450 degrees C. I had been designing my system to 600 plus C, thinking to get all the water out of hydration, hydrated mineral requires 600, 650 degrees C. Well, 450 gives me like 80% of that, if not better, 85%. The other thing that we saw was above that temperature, you start driving off hydrochloric acid and hydrogen sulfide, things that I really don't want to have to deal with. So by dropping my temperature below 450 degrees C, I get the bulk of the water without the problems that occur later on. This is the type of data that we want in that prospecting phase to help us design economically our resource prospecting systems. And then the last thing is, I think I have two charts that I'd love to show. One is Moon ISRU, Mars ISRU. Completely different environments, completely different resources to begin with. How are they the same? Well, when you break down the technologies that are used, even though I'm going for the atmosphere on Mars and maybe the soil, and I'm working with regolith on the Moon, it turns out a lot of the technologies are used across the board. The other thing I like to show is, here's that same list of technologies, here's my ISRU, but here's all the other people that need those same technologies. And when I show this chart with that other chart that shows how do we combine all those systems together, we're starting to get a lot more people kind of nodding their head going, that's a good approach. Now I'll stop.
All right, we'll have questions.
So we actually have apparently audio-visual thing that needs to be taken care of.
Right, but let's have 5 minutes of questions, and we'll break to do the audio-visual fix.
I got one better schedule at the very end there. Rounding off the numbers, with 22 years, I'm going to round it up to 24. We're talking anywhere from 3 to 6 different presidential occupants of the White House, 6 turnovers of the Senate, 12 turnovers of the House of Representatives. How do we get the money out of all these different people?
I guess I look at it differently. I like to joke with some of my colleagues that working in ISRU over the years has been likened to a drunk stumbling across the room in the dark trying to find the door. Eventually you'll get to the door. Sometimes you fall, sometimes you stagger different ways. I can't talk for the whole program. But with respect to ISRU, for example, the approach that we've been taking is if I identify those common technologies, if today, you know, and for example, working under Constellation from 2005 to 2010, that was all lunar focused. Mars was not even in the equation. So we worked on those technologies knowing that if Mars came back, the bulk of those things would be ready for, oh, by the way, I'm going to take off my lunar hat, put on my Mars hat, here's my design. So to a certain extent, I agree with Bob, you need to have a focus, you need to have a plan that's laid out. And the sad thing is that the Constellation program was actually a bipartisan program. Whether we agreed with the approach or not, the White House, the Senate, and the House all agreed to the vision of the Constellation program and was going forward. Presidents like to put their own stamp on things. Political parties like to put their own stamp on things. Sadly, NASA is a political organization. Personally, this is not NASA speaking, this is myself. I see a game change in how things are done with the introduction of commercial space. And I think that is the potential difference between what we've been doing in the last 20 some odd years and to where we may be going, is that commercial space in some cases is driving the bus, not sitting there. You, yeah.
What ratio are you proposing? Is it a 3 or 3.5 for LOX LCH4?
Whatever the propulsion system wants. It turns out that if you have water and carbon dioxide on Mars, you make it a 4-to-1 mixture ratio. So
Okay.
I can scale down to whatever the propulsion folks want.
You mentioned 50 tons there. That means you've got 200 tons of propellant. What size vehicle are you talking
No,
about?
I said 25 metric tons of oxygen.
Okay, so
for
that's
asset.
going to take you 200 then, I'm sorry. That's still a large vehicle just to get it into orbit. It's not going to, you're not going to get a transorbital injection. What's,
No, it's going up to Mars orbit, a high Mars orbit.
okay.
It's not a direct return.
How many tons is what I'm talking about?
Oh, what's the capsule being launched into orbit? To be honest, I don't know. They try to minimize it as much as possible, so that brings down the propellant. I just know for the design reference architecture 5, they needed 23.8 metric tons, plus I made a little extra for backup for life support.
It's probably about a 6-ton capsule.
Thank you.
Yeah. I think around 2012, a paper came out showing the probability of water ice deposits in the near surface regolith on north-facing slopes as close to the equator as 25 degrees. So if you had a source of water that you could essentially strip mine, just like you would do on the moon at one of the poles, and turn that water directly into hydrogen oxygen, it would make sense to localize specific landing sites with regard to both the water supply and other minerals that would be useful. So is there any current restriction due to things like hydrogen embrittlement and so on using oxygen, hydrogen fuel on Mars as well as oxygen methane, acknowledging that oxygen methane is quite a viable solution, but you can't get your vehicle back down to the surface if you use methane. You can get it back up to orbit, but you can't bring enough methane up to get it down to the surface again.
You mean a up and down?
A reusable vehicle, because then you could make multiple trips and bring a lot more supplies
the
and equipment
problem-
down.
When you look at oxygen and hydrogen, it looks great on paper. In reality, the volume of oxygen, hydrogen ascent, descent stages is so huge, it is hard to package. And so, especially for Mars ascent, we looked at it just recently, a comparison of a LOX hydrogen ascent vehicle versus a LOX methane ascent vehicle. And even with the extra performance that you get from ox hydrogen, it grew bigger, the mass of the vehicle became bigger. It just wasn't attractive. Now, you bring up other points about the viability of the propellants. That's, maybe in the future we'll come up with ways of wanting to do a reusable up and down system. I think the first step is you know, just the up, personally, and I believe water resources will play into landing site selection. As I pointed out, there's lots of different water resources. Now it's a function of the difficulty and the mass of the hardware associated with it. Is going for a higher concentration of water on a slope that requires me to maybe come up with a very interesting, unique mining method, better or worse than a system that just digs up the soil near the surface at a much lower concentration. That's an economic study that's worthwhile pursuing.
If you
All right,
want-
one last quick question.
I'll let you.
Sir.
I have a quick question. Did you consider the possibility of utilizing 3D printing technologies so you can utilize regolith or other local materials for many possibilities like construction, or you can even print parts, component parts of some other equipment?
Yes, I purposely didn't go into that in this presentation since I wanted to focus mostly on the propellant aspects and what we've been primarily doing. Significant work is going on in that area. I believe ESA, the European Space Agency, has a funded program for kind of building a 10 meter by 10 meter type of structure. We are looking at civil engineering aspects. A lot of work had been done in the past on lunar concrete using molds, and I think now that with 3D printers, you're going to start seeing a look at what did we do 20 years ago, and how can that be inserted in the new technologies? What type of binders? Do I need any binder? Can I use the laser from a 3D printer to sinter the material solid, or do I need to mix it with something else? That's just starting. So we haven't gotten very far.